This is the 28th video on a series on single agent search. And in this video, we are going to build on what's been going on in the last few lectures, talking about heuristics and pattern databases in particular. And we're going to show how we can use neural networks for compression. So neural networks are fairly hot right now, and a lot of people are using them, deep neural networks and other things like this for quite a lot of different applications. And people have tried to use them for doing learning in heuristic search problems before. And there's been some press about certain papers that have been written. But if you look at these papers, none of them have any solution quality guarantees. And a lot of them they're not coming from people who have a deep understanding of heuristic search. And so it results in a heuristic, unless, for instance, if you learned something on, let's say, the Rubik's Cube, unless you test it on all states, you don't have any guarantee that you can actually solve all problems in the Rubik's Cube. Or you do something where you're going to get some coverage guarantees or things like that. So we've known that and these are nice things that they tell us that we have this ability to learn something about a state space using a neural network, and we can use them for solving single agent problems. But if I want to be able to use the results here in a little bit more methodical, anyway, if I want to use these results in a little bit more of a careful way, where I can make strong statements about what I am able to do and why I'm able to do it, for instance, find optimal solutions, then it's going to require a little bit more work than just putting a neural network on the problem and declaring success. Now, there has been some work. There was some work about 15 years ago that was able to, it was an engineered system that was able to take a neural network and it was able to learn an admissible heuristic. But the system that is described there was a system that used, and this was by Mehdi Samadi. It was a system and some co-authors as well from, he was a master's student at the University of Alberta at the time. And so he put together like a decision tree, and he used a special training methodology where he split the data up into different sets. And when he split it up into sets, then he could, he had a loss function that was allowing him to try and penalize overestimation and things like this. And it was a technique that overall worked, but it didn't use maybe the more modern mechanisms for training that we have today that, of course, may someday themselves be outdated. But it also required a lot of engineering of like, how am I going to divide this state space up, and what am I going to do to, put other classifiers on the problem and things like that. And so the goal here, and just to be clear, this is the work of my master's student. As the date that I'm speaking here, it has yet to be published, but it may be, we may expect to see this hopefully in the near future. So I want to describe some techniques here, and particularly one of them will allow us to build a single neural network which can learn a large heuristic and can learn it accurately. In fact, can learn it more accurately than we would get by taking a compression of a large pattern database. And I'm going to just go through some of the ideas here. And I think some of the important things here to take away, so I'm not going to be able to give an entire background on neural networks and everything that's going on there, but the takeaway is that if we understand heuristic search, and if we understand, then we're able to apply that understanding to be able to get neural networks to do what we want, that is learn an admissible heuristic. Not necessarily consistent, but we'll get to that. But learn an admissible heuristic that then we can do something more strongly with. Okay, so what we're going to do is we're going to turn this into a supervised learning problem. And it's going to be supervised learning from a PDB, a pattern database. It could be from any other heuristic, but and really what it is it's a table-based heuristic. So as long as my values all come from a table, then I don't really care if it's a pattern database or something else. But the point is, you give me a table of numbers, and in practice, you give me a table of numbers. I'm going to give you a neural network that will be able to take that table of numbers, and we'll be able to produce an output which is no greater than that table of numbers. So it'll still be admissible, but the amount of memory that's required to store the pattern, the neural network, will be much smaller than it was required to store that heuristic. Now, one thing we may immediately say is, well, we're doing supervised learning, and that means you have to build this pattern database. And if I have to build the pattern database, then, why not? Like, why should I be building these pattern databases? Why not just use the pattern database, for instance? And the issue that we have here is that we can build pattern databases that are much, much larger than any memory that we have. So to my knowledge, the largest pattern database that has been built is I think it was about 2.6 terabytes. The Rubik's Cube. And so that's 2.6 terabytes. Like, we just don't have that much memory. But there's a lot of information that is stored inside that pattern database. And so we'd really like to say, hey, if I'm going to have this 2.6 terabyte pattern database, maybe there's something I can do with it. And just to be clear, this was built using a external memory search. So a couple lectures back, external memory. A couple lectures back, we talked about external memory algorithms. We talked about doing breadth first search and implicit state spaces. This is exactly an example of this, where we build a pattern database for Rubik's Cube that is able to fit on disk, but it doesn't actually fit in memory. And so now what we'd like to do is say, well, now can I use things like neural networks to be able to compress these? Okay, so that's the first thing we're going to do in terms of the approach. The next thing we want to look at is that there's two types of ways that we can do learning. There is regression. And what regression is, it's trying to learn a function. So it's a numerical output. And then in addition to regression, there's classification. And classification it's still a numerical output, but it's interpreted as classes. So we end up with class labels. And we'll talk about exactly how we determine what class label we choose, because we're going to modify this slightly to make sure that we get an admissible heuristic. So what we're going to do here is, again, previous work was using regression. We're going to go ahead and use classification, because classification is going to, sorry, I spelled labels wrong. Classification is going to help us out because with regression, there's always this possibility that you get an outlier that gives you a heuristic of 100 on a state space where maybe the maximum heuristic is 10. And you could try to clamp that or something like that, but maybe an easier way to do that is just to use a classifier where I have class labels. Now, the immediate thing you might be thinking here is, well, how many class labels do I have, or how many class labels can I handle? And so the next thing we're going to use, and I'm not going to describe this here, it's in the previous lectures, but well, maybe I'll just say something briefly, is a delta heuristic. So if I use a delta heuristic, take a small heuristic that fits in memory, and I subtract that from my very large heuristic, then what it's going to do is it's going to be able to significantly reduce the range of values that I have. And so this is going to give me a smaller label set. Okay, so delta heuristics will be very helpful for using our neural networks here, because they're going to make, instead of having 39 classes, we might be able to get down to having 11 classes, and that's going to be a much easier learning problem. Okay, and these are the basic things that we're going to do, and then we're going to look at two different approaches that can be used on top of this that will allow us to guarantee that we have an admissible heuristic. And so we'll look at these. And so one of these has to do with quantile tuning. And the other one, which we'll do on the other side over here, has to do with ensembles. Now, for the sake of this video, I'm not going to give a complete introduction to neural networks, but we're just going to think of them as it's a black box. I give it a table of numbers, and I say memorize this table of numbers, and it's going to try and memorize that table of numbers. And so it's going to, on some of them, it's going to do the right thing. On some of it, it's going to do the wrong thing. But we're just going to say, hey, go try and do that. See what you can do. And it's going to come back and, depending on the number of layers and, the architecture and whether it's convolutional neural network or other things like that, it's going to have some level of success in doing that. But we expect that actually it's not going to be 100% successful in producing an admissible heuristic immediately. And so this is where it comes down to this question of classification, and particularly, how do I determine a class label? And so this is what we want to look at here. So what is the output of a neural network when we're doing classification? What the output is a number of classes. And I'll make this really simple. Let's just say we have 3 classes. And what I can have here, for instance, is these classes may correspond to a heuristic of 0, a heuristic of 1, or a heuristic of 2. So those are all valid heuristic values. They may be all, well, some of them may be admissible, some of them may be inadmissible. And the idea is I'm going to put a weight on each of them. And typically that weight is normalized so that the sum of the class weights add up to 1. So that these can be interpreted as the probability that a particular weight is, or a particular class is going to be the correct heuristic value. And there's a number of different ways that you could choose which class you want to have. So for instance, you might choose the class with the maximum weight on it. So what might happen is I might have a weight of 0.33 here, a weight of 0.33 here, and a weight of 0.34 on 2. But if I look at this then, and I tried to say just take the class with the maximum value, what you see here is I'd predict 2. But practically speaking, from a probabilistic view, we might say, well, there's actually 2/3 chance that the heuristic is 0 or 1. Now, in practice, because this is a supervised learning problem, and I didn't say what the supervised learning problem is, right? The supervised learning is, well, I did say it, but I didn't connect it, is just learn from the table. So we know what the input is, and we know what the output should be for every input. And so when I look at this, I might look here and say, well, I'm going to predict 2 because that's the maximum value here, but maybe I should do something smarter. And so you could say, well, choose the first value that has half of the probability mass. And so that would say, well, always choose a value of 1. Or you could come up with other rules here that would say, what should I be doing for choosing the value for my classes? And the approach that we're going to use here is we're going to choose a quantile. And what we're going to choose basically is for every state. So what we have is, imagine here, I've got one state, let's just say the sliding tile puzzle, whatever the values are here, I don't really care what they are. The details of what they are doesn't matter. I stick this into my neural network, which is my black box, and my black box is going to stick out a set of values here. And let's just say that the correct heuristic is a value of 1, because I know this is a supervised learning problem. And I look at my classifier and it says, well, you know what? I'm going to put a 0.4 weight on 2, and I'm going to put a 0.3 weight on 1, and I'm going to put a 0.3 weight on 0. Okay. And so this is, again, a reasonable distribution, and we might want to predict a value of 0.4 here. But what we can do is we can say, well, you know what? What I'm going to do is I'm going to choose a quantile. That is, I'm going to choose an amount of probability mass, and I'm going to predict whatever the first value is that has exactly that amount of probability mass. So for instance, I could say, if I said my quantile is equal to 0.5, then the value here that I chose, well, 0.5 is this 0.3 plus 0.2 of this. 0.5 is in the value for 1. And so my prediction, my output would be 1. If I set my quantile to be 0.2, then the output would be 0. And what I can do is basically I can go through my entire pattern database. I can go every state there. I can put that state into my state space, into my neural network, and I can look for that state, what quantile is required to give me a heuristic that is admissible. And then all I have to do is say that the heuristic, or the quantile that I'm going to use, I'm going to call that Q star. And all I want it to be is so for each entry, I'm going to take the minimum quantile, I'm going to take the maximum quantile, which gives me an admissible heuristic, and then I'm going to take the minimum over all of those. So this is the min over over the Q for each state. So I could write this in a couple different ways, but we can just think of it's the Q, so it's the min over all states in my entire state space of Q for that state. And I should have a function for this. I didn't write down a name for this, but it's the minimum of Q, which leads to a admissible heuristic. Okay, and so I want to know over all states, what is the minimum Q that results in an admissible heuristic, and the minimum over all possible Q. So each Q is the maximum value that would give me an admissible heuristic. So in this case, if they were supposed to be 1, then like 0.6, or it depends on whether I have a less than or equal to or something like that there. But anyway, so something like 0.6 here would still give me a heuristic of 1. And then, so I'm going to get the maximum value that gives me an admissible heuristic on every individual state. And then over all states, I'm going to take the minimum quantile, the minimum of all of those quantiles, and that's going to be my Q star. And so what's going to happen is there may be some state out in the state space that requires me to use a quantile of 0.1 and in order to be admissible on that state. And so for this state, I will have some loss here because I'm then going to predict a value of 0 when I should have predicted a value of 1. Okay, but the idea here is I've got this quantile. I'm going to do this computation of what quantile I use for prediction by looking at all states. I'm going to find the quantile that produces an admissible heuristic, the maximum quantile that produces an admissible heuristic, and then I'm just going to say, here's my neural network. So now I can give you a single neural network. I can give you a single quantile value, Q star, which is the minimum over every state that produces a admissible heuristic. And then you asked me to get a heuristic for you. I take a state, I look it up, and I go look it up, and then I get the value from that, and it tells me what the heuristic is coming back from the neural network. So that's our first idea here. And this, depending on the state space, this can work really well on its own. And when I get to ensembles, then we're going to look at something a little bit different. We're going to imagine here, so you can imagine this is my table. And I could say, ask this question, like of all the states that are in the state space here, which of these values did I produce inadmissible heuristics for? And what we did here is we said, well, for all the values, we're going to tune the quantile that I use to make sure that's admissible. What we're going to do here is we're going to do a training process where we're going to train neural network 1. And once we've got neural network 1 here, we're going to take the remaining red entries and we're going to use just those entries to train neural network 2. Now in practice, we actually might throw in some of the other values that are inside here, just because by throwing in some of those values, we might be able to improve the quality of our heuristic. But practically speaking, we're thinking about, hey, I'm going to keep these values, I'm going to copy them into, or those are the only ones I'm going to train on my next state space. And what's going to happen here is if we assume that we're always going to be able to learn at least one new state, then every time I do this process, I train a neural network, I find the ones that are overestimated, and then I take those states and I try and train my next neural network on those states. And then I just keep repeating that process. As long as one new state is learned in every step, then in practice, I'm guaranteed that eventually I'll be able to, I'll have learned the value of all states. And what my heuristic is, so my heuristic is equal to the min of the heuristic from neural network 1, neural network 2, and so on. Because what I know is that this neural network, who knows what it's produced on the states that I didn't train it on, but I know that this heuristic is admissible. So if that heuristic is admissible, then the min of these two will also be admissible. Okay. So the idea here is I'm going to just build a whole bunch of an ensemble is what they're called. And this is a technique that dates back quite an old idea within machine learning, way before the sort of modern GPU-based or TPU-based training and things like that, was this idea that we could do ensemble learning. And here we're going to use ensembles where I take the min of all of my ensembles, and that's going to be able to, by doing this over a bunch of neural networks, that's going to guarantee that I can get an admissible heuristic. Now, there's a couple of things here we can do in practice to make this a little bit more effective. As I said, training on some of these values that I already learned properly can help with the training on the next step, gets more accurate values. And so like that's useful. We could also combine the two of these things together because I could use a quantile along with my ensemble. So I could have a quantile for each of these that try and maximize that. And the other thing that I can do is I might be like when I'm building a table here, I might discover that, well, what we did discover when we did this in practice is that maybe my second neural network has actually just learned the whole problem better than the first one has. So I could throw away the first one and just use the second one. But in practice, we found that we could oftentimes, for the problems we looked at, which were up to 500 million entries. So, on the order of 1 billion entries, that we were able to use just 2 neural networks to be able to learn admissible heuristics. And so ensembles are a second technique that if we think about what we've learned about heuristics, like we're thinking about the min and the max and other pieces like this is just an idea that says, hey, if I train multiple heuristics and I know that some of them are going to be overestimating, as long as I take the min, so if the min overall is not overestimating, then I just take the min. And here what I'm going to do is when I get any given state, I'm going to look it up in every heuristic in my ensemble, and then I take the minimum of all of those as my actual heuristic value. We can validate ahead of time that this is then an admissible heuristic, and so then this is another way that I can take my neural networks. I can use them where they don't necessarily have predictable values, but I can get a predictable value out of it, namely an admissible heuristic. And as I said, we can combine them both together. The only last caveat on top of this is that neural networks can be a little bit expensive to do this lookup in them, especially if we're like sending it from the CPU to the GPU and then coming back, things like that. So it can be more effective in practice to look up many heuristics at once. And there's fairly straightforward modifications we can make to our algorithms like IDA star, A star, to batch the lookups of heuristics so that we can look a whole bunch of heuristics up at once, and therefore we don't pay an overhead of looking one state up at a time. But I'm not going to have time to talk about that here. But what I just wanted to give here was a relatively short overview that says, look, if we understand these techniques of heuristic search and the idea of like using the min of values, the idea of using deltas and things like that, then we can combine them together with an understanding of neural networks, and we can put together some nice ideas here that allow us to learn admissible heuristics using neural networks. There's still a lot of work to be done here to try and scale this. Like we can't yet solve this, learn this 2.6 terabyte Rubik's Cube. So we'd like to be able to, ideally, we'd be able to go and actually learn this and be able to use that much smaller. And even, how do you take a pattern database this big and even do training on it? Because that's going to take a significant amount of time. So there's lots of interesting questions here of what can be done. Maybe there's more techniques that can improve this process. And that's really an open research question. So maybe someone is going to want to take that up and see what they can do. And actually what I haven't talked about here is from the learning side. I've seen lots of recent learning theory that talks about like maybe we want to use different learning techniques if we're doing supervised learning. And here we're not worried about overfitting. So maybe there's modifications we can make to our learning algorithms because we're not trying to generalize beyond sort of the entries in my pattern database. So maybe I don't have to worry about overfitting as much as I would in a classifier for a medical application. And that'll allow me to, maybe I could learn much more quickly as a result. So there's lots of interesting open questions here, and we'll see what happens in the future with being able to sort of look at what happens when we merge together some of things like machine learning and heuristic search. I guess the last thing just to say is that this technique is really trying to get neural networks to shoehorn into the heuristic search framework. And there is a question going the other way. How do I get my heuristic search framework to work with some unreliable data like a neural network? And there is some interesting work that's been done to start that out by Roni Stern, but I think there is more work that could be done there as well.